Okay, hello everybody. This is Dr. Gerstel reporting back to you for game theory. This video is for take the place of Wednesday's class this week. And before I get started, how do you make the number 7 even? You make 7 even by removing the s. So anyways, in the last video we talked about looking for dominant strategy Equilibria in looking at games, and how some games will have them, like the standard prisoner's dilemma, and other games will not, like our iteration path game, as well as the uneven prisoner's dilemma. Neither one had a dominant strategy equilibrium. And so what I would like to do in this video is to talk about a different definition for equilibrium that's a little bit more broad than the dominant strategy equilibrium we used last time, where each player has to have a strong or weakly dominant strategy. And in this video, we're going to be talking about the iterated dominance equilibria, where in general, an iterated dominance equilibrium is going to be a strategy profile that can be obtained by first you take a strategy for either player that is dominated by another strategy, and you just remove it. Cross it out from your game, pretend it doesn't exist. And then you basically just keep repeating the process. You say, all right, out of what's left, what's going to be dominated by a strategy, and you can go for either player in either order in doing this, and strike it out. And you basically keep repeating the process until what's left is just a single strategy for each player, and then that combination of strategies, that strategy profile, we're going to call an iterated dominance equilibrium state. So let's take a look at our iteration path game from last time. Write that in here, iteration path game. And see if we can find an iterated dominance equilibrium state in this game. And so, if you recall last time, we said in the video that if you're player 1 and player 2 playing this game, what's likely going to happen is you're going to end up in this top left or this top right corner due to the fact that player 1 should always pick dying, and if player 1 picks dying, player 2 should pick either eat or love. And what I would like to do is to now make that thought process a little bit more formal. And so, if we're looking for iteration dominance equilibria, the first thing I'm going to do is I'm going to notice that for player 1, dash as a strategy is dominated strongly by dying for player 1, because no matter what player 2 chooses, eat, pray, or love, dying is going to give player 1 a better payoff, a strictly better payoff than dash. So first thing I'm going to do is I'm going to remove dash for player 1, as it is strongly dominated by dying. And so what I'm going to do then is I'm going to go cross it out. Give it a swoosh. Not a swoosh swoosh, but a single swoosh. So now player 1's only left with 2 strategies, dying and sleep. And now at this point, we could go ahead and remove sleep as well for player 1, because it's weakly dominated by dying. But I'm going to take a break from player 1 for a minute and see if we can eliminate any strategies for player 2 to start with. And if you notice, I think with what's left, player 2 has 2 dominated strategies. Specifically, pray is going to be strongly dominated by love, because if you're player 2, if you pick pray, you're always going to get 10, but if you pick love, you'll either get 12 or 13. So in step 2, I'm going to say remove pray for player 2. And we can do that, swoosh. But we could also remove eat as a strategy for player 2. You might be thinking, but Dr. Gerstel, if player 1 chooses dash, then eat is going to give a better payoff than love. Yeah, but we've removed dash from player 1's profile, from player 1's strategy set. Dash is no longer an option for player 1, and out of the options player 1 has left, dine or sleep, love and eat are going to tie if player 1 chooses dine, but player 2 is going to be better off if player 1 chooses love, because 12 ties 12, but 12 loses to 13. And so with what's left, after we've recalculated, eat is going to be weakly dominated by love. So I'm also going to put in here, we're going to remove eat for player 2. And both are going to be dominated by love. So cross that out as well. It's good. Prey is going to be strongly dominated by love, and eat is going to be weakly dominated by love. And so now, player 2 only has a single strategy that's left, which is love. And now player 1 has a couple of choices. They can either choose dine or sleep. And I claim that out of what's left, one of these is going to be dominant for player 1, and that is going to be dine. Because out of what's left for player 1, if they dine, they're going to get 1. If they sleep, they're going to get 0. So we're going to remove sleep for player 1, because now it is strongly dominated by dine. And once we do that, if you notice, we only have a single strategy left for player 1 and for player 2. That being player 1 chooses dine, player 2 chooses love. So that's going to tell us that the strategy profile of dine love is an iterated dominance equilibrium in this game. Meaning, by continually deleting strategies for each player that are strongly or weakly dominated by other strategies, and continually recalculating, we can end up with dine love being a single strategy profile in this game. Dr. Gerslow, I thought you said player 1 is going to, I thought you said dine eat was also a likely strategy. Let's see what happens if we try this process again, but we eliminate strategies in a different order. This time I'm going to use this version of the table. So first thing we're going to do is, if you notice, we could say, last time we started by eliminating dash for player 1. Let's say this time, just for the heck of it, we want to remove sleep for player 1. Because if you notice, as a strategy for player 1, sleep is going to be weakly dominated by dine. If player 2 eats, dine is better. If player 2 loves, dine is better than sleep. If player 2 prays, dine and sleep are going to be equal to each other. So first thing we're going to do is we are going to remove sleep this time for player 1, because it is going to be weakly dominated by dine. And now, second, what are we going to do? We're going to notice that if we move on to player 2 now, we can also remove dash from player 1, but we're not going to do that, and I'll explain why here in a couple of minutes. If we look now at what player 2 has left, I think player 2 has a couple of strategies that we can eliminate. Specifically, we know prey is going to be strongly dominated by eat, because 10 loses to 12 in either case, no matter what player 1 chooses. So we're going to remove prey for player 2. if we notice though, love is also going to be weakly dominated by eat. Because if player 1 dines, love and eat tie for player 2, 12 ties to 12. But if player 1 chooses dash, 11 loses to 12. And so in this case, eat is going to weakly dominate love. So we're going to remove love from our table. Because they're both going to be dominated by the strategy of eat. So swoosh and swoosh. And now, if you notice, with what's left, player 2 has settled on eat as their only strategy that's left. With player 1, they can now choose between dine and dash. And dining gets them 2, dash is going to get them 0. So we're going to remove dash, excuse me. Forgot to mention this is for player 2. And we're going to remove dash for player 1 because it is strongly dominated by dine. And so what we're going to be left with is dine eat is going to be the only strategy profile that's left. Player 1 only has dine left as a strategy. Player 2 only has eat left. And so that's going to tell us that dine, eat is also an iterated dominance equilibrium. Sorry, getting a little bit cramped here, but I just wrote on the board, dine, eat is also an iterated dominance equilibrium. So if you notice, the order in which we eliminated strategies in this game was actually important, because one way in which we removed strategies from the two players left dine, love as our iterated dominance equilibrium state. And another way that we remove strategies by removing in sort of a different sort of order left us with dine, eat as our iterated dominance equilibrium. So the moral of the story is, unlike with dominant strategy equilibria, it's possible for the same game to have multiple iterated dominance equilibria, like this iteration path game. Let's check one more time. Before I move on and talk about the two versions of the prisoner's dilemma, I could sense that someone has a question. Yeah, Kate, what's your question? Ooh, Kate has a good question. In that Kate just asked, what if we started by removing both dash and sleep for player 1? That's a fair question. I'm not going to rewrite out the table because I'm out of room on the board. But let's say we did it a third way. We could start by removing both dash and sleep for player 1. So remove dash and sleep for player 1 because they're both going to be, they're both going to be dominated by dine. So if I erase the lines I've already drawn here, I'd say what, I'm just going to redraw this table. Go ahead and skip a few seconds forward in the video while I go ahead and redraw this table out here. Let's see. Dash. Zero, 12, 110, 0, 10, 110, 112, 0, 11. Okay, I'll come back now. So what we're starting by doing in kind of our third attempt to find iterated dominance equilibria is we're going to start by removing dash and sleep both as strategies for player 1. By the way, if you're doing this, you could start by removing a strategy for player 2 instead. It wouldn't be wrong to do that. But I'm just doing it for the sake of it. Let's see what happens if we start by eliminating dash and sleep for player 1. So if we take a look now at what's left, player 1 only has a single strategy, which is dine. Player 2 is not going to choose prey, because prey would be dominated by, I don't know, take your pick of eat or love. This one gives you 12. That one also gives you 12. So now we can remove prey as a strategy for player 2. And it's going to be strongly dominated by both eat and love. And now, player 2 has 2 strategies left, eat and love. Which one can we eliminate? See, that's the tricky thing. We can't eliminate either of the strategies because out of what's left for player 2, eating and loving give them the exact same payoff. Eat doesn't dominate love with what's left, and love doesn't dominate eat with what's left. Because player 2 gets the same payoff either way. So at this point, we're stuck. We can't eliminate anything. So what does that tell us? No, it really doesn't tell us anything. Just because we got stuck doesn't mean dine eat and dine love aren't iterated dominance equilibria. It just means that the order in which we eliminated strategies didn't get us there. And that's something that can happen when you're looking for iterated dominance equilibria like this, is if you could end up just getting stuck if you get unlucky and sort of eliminate strategies in the wrong order. There's no way for us to really have known that if we had removed strategies in this order, that we'd end up stuck like this, but dims the brakes. So this doesn't tell us we don't have any iterated dominance equilibria, because obviously we already found 2 of them by eliminating strategies in a different order. It just tells us that we should retry going another way. All right, Trudy, what's your question? Okay, Trudy was asking, how can we know if we can, how do we know when we can stop? How do we know that there's not another way of doing it that would produce a 3rd strategy profile as an iterated dominance equilibrium? And it's a good question, Trudy. You know, I don't like the disrespectful tone in which you asked it. In general, the way you know when to stop is, if you see any strat, is you basically kind of got to follow your nose and basically say, well, we know any iterated dominance equilibrium is always going to have dine, for instance, for player 1, because dash and sleep are both dominated by dine in the full, even in the full table. And if player 1 is going to choose dine, obviously player 2 is not going to choose prey. So eat and love are kind of, so dine, eat, and dine, love are kind of the only 2 possibilities for profiles that could be iterated dominance equilibria. And the fact that we determined that, yes, both of these are, means we can stop now. Nothing else really could possibly be an iterated dominance equilibrium state. Okay, so now that we've looked at this example, I want you all to pause the video here for a couple minutes, and see if you can find any iterated dominance equilibria in both the standard prisoner's dilemma as well as the uneven prisoner's dilemma, the one where prisoner 2 gets to make their decision with knowledge of player 1's. Let's go ahead and pause for a few seconds, see if you can find any iterated dominance equilibria in these 2 games. Don't worry, I'll wait. And when we come back, we'll talk about looking for them. So pause. Pause. Okay, you can unpause now. And if you notice, in this first game, well, deny, if we're looking for iterations, then first thing we can do for player 1 is we can cross out deny, because deny is strongly dominated by confess. So we're going to remove deny for player 1, because it's strongly dominated by confess. And we can do the same thing for player 2. We can cross out and remove deny, because it's also strongly dominated by confess for them. So we're going to remove deny for player 2, as it is strongly dominated by confess. And lo and behold, what's left for each player is just going to be confess. And so that's going to tell us that confess is going to be an iterated dominance equilibrium state. But Dr. Gerstle, I thought you said confess, confess in the standard prisoner's dilemma was a dominant strategy equilibrium. Yeah, it's also a dominant strategy equilibrium. But it could be both. And in this case, this strategy profile, confess, confess, happens to be both, fit both definitions of equilibrium that we've seen so far. And in fact, here's a tidbit for you, because I can hear Jack in my AA section. Jack's raising his hand and about to ask, isn't it always true, Dr. Gerstle, that a dominant strategy equilibrium has to be an iterated dominance equilibrium? And my answer to you, Jack, is, what makes you say that? Well, Dr. Gerstle, isn't it the case that if you have a dominant strategy, you can immediately cross out all the other strategies for that player? And if you do that for each player, to get a dominant strategy equilibrium, that's essentially doing the same thing as crossing out in order to get an iterated dominance equilibrium state, Dr. Gerstle? Very good, Jack. That was well explained. See, Trudy, you could learn a thing or two from Jack. So yeah, it's actually going to be the case in any game that if you have something that is a dominant strategy equilibrium, that is also going to be an iterated dominance equilibrium as well. So, and that's true not only in this game, but in any game. Any game that has a dominant strategy equilibrium, like the standard prisoner's dilemma, that is also automatically going to be an iterated dominance equilibrium, but not vice versa. Because, for instance, in the iteration path game, we had two profiles that were iterated dominance equilibria that turned out to not be dominant strategy equilibria. So dominant strategy implies iterated dominance, but not vice versa necessarily. Okay, so last thing I want to do is I want to look at the uneven prisoner's dilemma and see if we can eliminate strategies in a way that would get us with a single strategy left for each player. And first thing I'm going to do is, we know player 1 doesn't have any right off the bat strategies that can be eliminated because deny is strictly better if player 2 mirrors and strictly worse in every other possible case for player 1. So player 1, we can't cross anything out yet, but for player 2, I think we can cross some stuff out. And if you notice, confess, we said was a weakly dominant strategy for player 2, which means always confess, the second strategy here, is going to be something that that's going to strongly dominate deny, weakly dominate both the mirror and anti-mirror strategies. So we can immediately cross out everything but confess for player 2. So here we can remove all strategies but confess for player 2, with the idea that all of those other strategies are either weakly or strongly dominated by just always confess. All are dominated by confess. And now, well, player 2 strategy has to be confess then. What's player one's strategy going to be? Well, they can deny or confess. And if player two is confessing, player one can get a payoff of -8 by confessing or -10 by denying. So now we can eliminate this top case for player one and say remove deny for player one, because after we've done this first step and recalculated, with what's left, deny is strongly dominated by confess. And that's going to tell us then that both players just always confessing is going to give us an iterated dominance equilibrium. So confess, confess, just like in the standard prisoner's dilemma, is an iterated dominance equilibrium. Unlike in the standard prisoner's dilemma, both players always confessing was both a dominant strategy equilibrium and an iterated dominance equilibrium. But in the uneven prisoner's dilemma, always confessing for both players happened to be an iterated dominance equilibrium state, but not a dominant strategy equilibrium. All right. So that gives us kind of a way to look at equilibrium states, and that's different from the dominant strategy equilibrium. In our next class, we're going to talk about a third type of equilibrium state that's even broader than iterated dominance, called a Nash equilibrium state, because there is a game that we've actually seen, that you may have seen, that actually doesn't have any dominant strategy or iterated dominance equilibria, that being the Hawk-Dove game from Homework 1, which if you didn't look at, you might look at that before watching the next video. And it turns out that that game has a third type of equilibrium state called a Nash equilibrium, and we will see that in the next class. All right, so I hope you all are still doing well, still staying healthy, and I will see you later. Bye-bye. Peace out.